Welcome everyone. The question that is shown on the screen, it is from the sample paper CBSE 2025. Question number 3 is a long straight wire of circular cross section and of radius A carries a steady current I. The current is uniformly distributed across its cross section. The ratio of the magnitudes of the magnetic field at a point A by 2 above the surface of the wire to that of the A by 2 below the surface of the wire. 4 options are given: 4:1, 1:1, 4:3 and 3:4. Okay, so this is a question from the Ampere's circuital law. In the Ampere's circuital law, basically it is used for finding out the magnetic field at any point, okay, for a current carrying wire or for a current carrying configuration. Okay, so this is the wire. Let us say this is the A. Okay, and if you want to find it out the magnetic field at the point P, okay, which is basically A plus A by 2. This is A and this is A by 2. So the R1, if you say, you can say that is 3A divided by 2. Okay, so for that purpose, if you consider an Amperian loop like this way, then Amperian loop basically encloses the whole wire. So in this particular case, if you apply this Ampere's circuital law, that is the cyclic integral B dot dl is equal to mu naught into I enclosed. In this case, that will be B. Obviously, B is tangential and dl is in the same direction. So B dl cos 0 degree becomes B dl. It is mu naught I. What is the value of the I enclosed? Obviously, it is I. So if you integrate this, then it will become 2 pi R1. Okay, that is circumference of the Ampere's loop, Amperian loop, mu naught I. So the magnetic field B1, if I just design it, then B1, that is at any point outside here at the point P now. So B1 is equal to mu naught into I divided by 2 pi into R1. So that will be mu naught into I divided by 2 pi into 3A divided by 2. If 2 cancels out, it will become mu naught into I divided by 2 cancels out. So we can say this is 3 pi A. 3 pi A. Now if you try to find it out the magnetic field at any point inside the wire, okay, any point inside this wire. Let us say this is the axis of the wire and at any point inside, let us say this is the point is Q now. Okay, and actually it is A by 2 in the question, but if I consider this is R2, here also you have to consider an Amperian circuital loop. Okay, then if we apply this Ampere's circuital law again, that is B dot dl equal to mu naught into I enclosed, then it will be B dl cos 0 degree, obviously for obvious reasons, because the dl vector and the B vectors are tangential and it is considered from symmetry. So mu naught. Now come to I enclosed. What is I enclosed? For I enclosed, we have to find it out what is the current density. Current density is J. J is equal to I divided by capital A. I is the total current. A is the radius, so pi a square is a cross sectional area. Now if anyone want to find it out what is the I enclosed, then it will be J multiplied by pi into A by 2 whole square, or we can say R2 square. Okay, so it is I divided by pi a square multiplied by pi into A by 2 whole square. So pi cancels out, a square cancels out, it become I by 4 now. It become I by 4 now. Okay, so that will become B integration of dl, since B is constant. integration of dl gives you 2 pi r2 and r2 is a by 2, so 2 pi a by 2. It is mu naught divided by I by 4. So b is equal to mu naught I by 4, 1 divided by this 2 and this 2 cancels out, pi a. So this will become, if I just denote it by b2, this will become mu naught into I divided by 4 pi a. Okay, so b1 is mu naught I by 3 pi a, b2 is mu naught I by 4 pi a. So it is said ratio of the magnitudes of the magnetic field at any point above the surface of the wire to the point below the surface of the wire. So they are asking about what is b1 by b2. So b1 is obviously mu naught I divided by 3 pi a. If you divide mu naught by 4 pi a, this will become 4 pi a divided by mu naught I. So after cancellation it will become 4 by 3, or the answer is 4:3. Thank you all of you.